Welcome, I'm Dr. Afaq, and in this video I show you how to model natural convection heat transfer in porous media using ANSYS Fluent. It is our model. We have two different temperature, the high temperature here and also we have cold temperature here. As you know, the temperature difference is driving force for the airflow in free convection. For the model, this example, let's mount to ANSYS Fluent. For the start the model, click on Fluent, right click on geometry, and we want to create a new model. We change unit to millimeters. So here we select millimeter, select z-axis and click on xy plane and click sketch. Click sketch 1. Here we create a rectangle. Okay. So now we convert it to the square. So click on dimension, click this line and also click this line. H1 is 1 millimeter, V2 is 1 millimeters. Okay, click on generate. And now here you see that we have a square. Okay, now click on concept, surface from sketches, select sketch 1, click on apply and click on generate. Now we have a surface, so we want to check or the analysis the fluid flow or the free convection in this domain. Okay. In this section now we want to create the mesh for our domain. So right click on mesh, click on edit. Okay, click on mesh, click on generate. It is initial mesh, so right click on mesh, click on insert, sizing, select line. So we select 4 lines. Okay, hold control and select all lines. Now here click on apply and we use number of division. We use 100 division. So click on generate. Okay, now right click on merge, click on insert and click face meshing, click on apply. So we select the domain and click on apply and now click on generate. It is our mesh. Now we want to define the boundary condition. So we select this boundary, right click. Okay, it is TH. Okay, and also this boundary, it is TC. Click on OK and generate and close the mesh. Now right click on mesh and click update. Now right click on setup, click on edit. We use 7 solver processes and also active double precision and click on start. Our simulation is a steady state, so we use SCD and also we active the gravity. Its value is minus 9.81. Okay. Now let's move on to models. Active the energy equation. Click on OK. For the viscous, we use lambda flow. Okay, and click on OK. Now let's move on to materials. Click on fluid and click on air. The density is incompressible ideal gas, so click on change and create and close the window. Okay, now let's move on to cell zones. Click on surface body. We active the porous zone and click on porous zone. Here we have two resistance for the flow in the porous media. So we have a viscous resistance and also we have inertial resistance because we have low velocity in our free convection. So we deactive or we do not consider inertial resistance. So also only we use or consider the viscous resistance. So we use this default value for our simulation. And also for the porous media, we use 0.8. And also for the heat transfer setting, we use a Cobrium thermal model that is consider the temperature for the porous media and the fluid flow is the same. Okay, now click on apply and close the window. Now let's move to boundary condition. Click on wall, click on TC. Okay, click on thermal, click on temperature. The TC is 300 Kelvin, so click on apply, close, and click on TH. Click on thermal and convert temperature, and the temperature for the hot boundary condition is 310 kelvins. Okay, now click on apply and close the window. Now let's move on to initialization and click on initialize. Now let's move on to run calculation. We use here 100 number of iterations. Now click on calculate. Okay, the run has been completed. So now let's move on to result. Here, click on graphic, click on contours. Here is our pressure distribution. So now we want to check the velocity. So click on velocity. Okay, it's our velocity distribution. Now we want to check the temperature distribution. So click on temperature, and here it is our temperature distribution. So it's about the density, so you can check the density also here. So it's about the density variation of distribution inside our domain. Thank you for watching the video.